All right. With that, I'd like to thank Chuck again and for all his many contributions to our well-being and our entertainment. All right. Greg Bailey from GreenArrays is going to give us an update.
Can you hear me?
We can hear you fine.
All righty then. Well, I don't have a great deal to say this time, so I'll try and keep it short and sweet. Our status is that we currently do not have a production customer, but we might before too much longer. Our friend Augustine has declared a goal of making an inexpensive kit for popularizing the chip, and it'll be interesting to see if he's able to pull that off. And so that's a potential volume customer. Unfortunately, the two prospects that we were courting this year did not turn out. One of them was an AI group that we've been talking to, since the beginning, since early 2021, headquartered up in the Boston area. And they had appreciated the potential of an array of nodes such as ours in making expert systems. Certainly not optimal expert systems out of cell arrays. The proper way to do a cellular automaton is in fact to build hardware specific to the problem once you've understood how you combine the incoming stimuli to produce an outgoing one. And I can see a number of ways of doing that that are a lot more economical than having the computer mechanize noticing a bunch of things, summing them, and deciding whether to say something else that other people can say. It's an interesting network communication problem, but it sure as hell doesn't require a general purpose computer in each one. Oh, hi, John. Didn't know you were there. Rival type. Oh boy, okay, it's nice to see you all. At any rate, they danced around with us for about a year and a quarter, and then finally gave us an agreement to sign, which was unacceptable. And subsequently, they found somebody else to do their work for them, and so that's all gone. It was an interesting exercise to realize what was involved in making a neural network and what optimally would be done to implement it, which nobody, I believe, has ever done. And so if somebody wants to pay us to do that, stand right in line here, and I'll tell you what we've been thinking and see if it's interesting to you. Meanwhile, there was another prospect that I spoke about last fourth day, which was the Teal live streaming glasses promoted by a nice man named Mark Poderis. And at that time, we were right in the throes of actively seeking funding. Well, what it turned out was that the people that would fund such things appeared to believe that it was impossible to accept that we might actually be able to do something. So we would have to show them a working prototype, which none of us had the money to do. And so the funding was not obtainable by Mark. And so he gave up on that shortly after the first of the year. It's too bad. He had a good point. And now that Zuckerberg is tripped big time with Meta, it's entertaining to think that we could have done what he was talking about if he just not believed he needed to put a supercomputer on your head, which after all, in terms of energy budget, is not feasible. But there you go. If anyone decides they want to do something like that in the future, again, stand in line right here. It was still a good idea then, and it's still a good idea now. Not everyone appreciates what you can do with our chips that you can't do with anything else, because most people still have not programmed them. I don't have any evidence that anyone, well, other than Stefan Mauerhofer and a couple of people in Europe and one man in Japan, has ever actually written code for our chips. So if you have, stand in line right here, let me know, because we haven't gotten any feedback from anybody who has. the fact that you can have a machine that can wake up and execute 2 instructions and be asleep again is unprecedented and unparalleled. And when those instructions cost, 7 picojoules each, and when being asleep costs only leakage, and when there's nothing else going on the chip, that also is not precedented, not paralleled. But there you go. If people don't appreciate what that means, I don't know how to penetrate their psyches. It's just the way it goes. So we'll continue making and improving our chips and hoping that we can find a good customer. And again, if you're a potential customer, stand in line right here. We want you. It was interesting to hear Bill talking about Win32 We also had to make an implementation for Win32 platforms back in the early 90s. NCR had required that we put forth on their Unix platform, which at that time was SVR4 Unix running on the best 386s available at the time. And after we showed them that, it took us less time in native Forth to send a UDP packet to another computer and get an answer from it. That would be another computer running our operating system, of course. Then it took to send a 1-bit message to another process in that 386 and get the 1-bit reply from it using Unix. That there was something strange about this, and there were some new clothes missing on the Emperor. The problem, of course, was the zillion context switches being made inside of the x86 and the cost of those context switches, which is high enough to motivate Microsoft to actually, to motivate Intel to actually build separate register sets, 2 of them in each processor, because their context switch is so damnably expensive that it's worth the hardware to have a whole nother register set for a different process ready to just trigger off without having to load all that shit back up. Of course, we don't do any of that. But again, what can you say? So at any rate, after satisfying NCR that they sure as hell did not want the hospital system that we were underlying to be moved to Unix, then just for the hell of it, I moved that Unix system over to Win32. And that only took a couple of days because, of course, as it turns out, the execution engine inside of Win32 looks pretty much exactly like SVR4 Unix. And as long as you're using the C library to do all of your I/O, there's nothing to speak of, and the COF file format is the same. And at any rate, it was a trivial exercise moving our Unix polyforth over to Win32. Subsequently, of course, we added a few things to it so that we could hook up to DLLs at will and hook up to the callings, the entry points in them at will when we found that we needed one. And so that served fairly usefully for places where we had to put something acting like a Forth system on a Windows 32 platform for the resulting, it's almost 30 years now because we did that in 1993. The sane Forth implementation, which is part of the new ArrayForth3 development system for our chips, as a matter of fact, is that same thing with embellishments, because we had to add some embellishments in order to put the CAD system on it. But the embellishment systems are there, and they're available to, except for the CAD system, to look at for free from the website. And incidentally, one of the fun things about it, for those that like Win32 Forth and would like to add something to it, there are about 13 or 14 blocks of code on that sane Forth system that know how to make PDF files. And so you might download it and search through there and find that stuff and see if you can move it over to that platform. It's kind of enjoyable because our method of doing it is incremental on the fly. You don't have to have a scratch file in order to make a PDF file. Everything that needs to be remembered till the end of the file is remembered, and everything that would be a forward reference is a forward reference because there is syntax in PDF to forward reference things. So in fact, there's no scratch file necessary. We just start spewing out a valid PDF file as soon as somebody starts typing. And when they're done, we blow some tables out at the end and we're finished. It's an enjoyable kind of a thing. And if you also are interested in something that is more aesthetic than simply plain ASCII text display in, say, a font like Courier. I have all the mechanism here to draw pretty pictures and everything. Just, again, make contact. At any rate, all that's there and it's free. And as a matter of fact, the latest things that we've done to our website were to post a new version of the Array4 3D version. The reason for that was mostly to do a bunch of stuff for the benefit of the CAD system, but it includes adding the printing PDF code. It was done a decade ago for other customers, and massively updating the documentation. There's 4 documents that have been updated as part of that same reposting. Also, we had an interesting problem, and it's why we, in fact, have completely disengaged from network solutions. Once upon a time, there was a thing called the Internet, and that was the does everything group back in the early 90s of the Internet infrastructure. And basically, the Internic was transformed into a corporation called Network Solutions, still in the 90s. Later 90s. And that was composed of the same people that had been the Internet staff, and so they knew what the hell was going on. So that was a good idea, or at least I thought it was, to support the Network Solutions by being a customer of theirs. And so they handled registration of domains. And later on, they also started providing hosting services, which, again, being loyal customers, GreenArrays went ahead and used. However, they've been reacquired a couple of times. One of the acquisitions was by web.com, which really dismayed me because we had to block a whole bunch of IP address space that belonged to web.com as sources of junk mail. And so all of a sudden, our venerable vendor was now sending its mail to us via all of this blocked IP address space. Thank you very much, web.com. But anyway, in the course of all that, they also managed to hire some people that really didn't know what the hell was going on. So, for example, in 2014, they deleted the GreenArrays website because they had this notion that it had been hacked. Of course, it hadn't been hacked. I had a backup of everything that was there, and it was the same. Nothing had been changed. It was just, stupidity in action. And so we got them to restore it, and everything was back except that they had also deleted our area on their SQL server. And at that time, we were giving a little course structure in using the chips, which was called the Array4 Institute. Well, we had decided to, just for laughs, employ a tool called ClaroLine that Network Solutions made available to implement that course. And everything other than the videos in the course was stored in the SQL server with no backup mechanism. And lo and behold, we lost our course outlines and we lost our quizzes that Charlie Shattuck had gone to the great trouble of composing. So that was kind of a dismaying thing. And finally, recently, there was enough spare time to at least put up the structure of those courses, again, the only 2 of them so far, on the regular website as a more transparent HTML environment. So it's still there now, and you can find those little series of lectures, and the only thing that's missing is the nice quizzes that Charlie wrote. So we may add to those lectures because it's not a bad thing to do. And now that it's much more accessible and congenial than it was via ClaroLine, it should be viewed by more people. So that's there on the GreenArrays website. Now, what else do we have to speak about briefly? We do have some chip design improvements in mind. And we have been basically laying them out and waiting patiently for an opportunity to commit them to silicon. And they haven't been because there has not been that opportunity. But they are examples of the kinds of things that concern us that don't necessarily concern everyone else. Remember, Chuck deals with the minutia. He starts with the minutia and builds the splendid stuff out of it. So we deal with pieces of diffusion and pieces of poly and pieces of metal and contacts between them all. And we look at these and we think about them and we measure them and we pay attention to what the time constant of each little piece of metal that we add is, because it's attached to things that have capacitance. It has capacitance itself, the diffusion it might attach to, or the poly it attaches to, all has capacitance, and that whole network has a time constant, and it's pretty hairy ass relative to the scale of things we're trying to do sometimes, especially if you let the metal be just laid out willy-nilly as a typical synthesis program will do. So we worry about all this stuff at the microscopic level, and that's one of the reasons that we're able to run instructions at least 3 times faster on a 180 nanometer process than is the conventional wisdom. Conventional wisdom being the maximum clock speed is going to be 200 megahertz. And here we are running instructions at 600 megahertz. So isn't that strange? Well, you get there by same old deal, going to first principles. What are we here to do? Make a computer. We're not here to make a computer that can be programmed by an imbecile. We're not here making a computer that can run terrorist code over in another process while it's doing what it's really there for. We are making a computer to actually execute some code and not waste resources and energy doing it. So the improvements that we have in mind, some of them are simply looking at those things over again. There's a trace of metal that goes from the top of stack register up into our whole memory array, carrying each of the bits of the address. And there's another bunch that contain, or excuse me, the address go from the address register. There are, again, 18 read and 18 write lines that go up into there from the top of stack register for data on memory reads and writes. And on the current F18A, we have the write line enabled all the time. And as a result, every time the top of stack register changes, all of those long lines going up into the memory change. Well, there's a lot of femtofarads on those long lines. And there's a lot of loads on those long lines, because those long lines attach to a lot of pieces of diffusion going up through the memory. So yes, we are using a hell of a lot of energy charging and discharging those lines. You can measure this if you program our chips and have bothered to learn how to measure energy through, being consumed by shunting the power supply into, say, the target chip and putting a good high resolution voltmeter on it. Try just running a micronext loop, an infinite micronext loop. To do that, you load up the return stack with all ones, all minus ones rather, and you run an instruction that says no op micronext micronext, and that will run forever. With a minimum of anything going on. It won't do any instruction fetches, won't do a damn thing at all. And you notice that one instruction in an infinite loop will consume a given amount of energy that you can measure. You can measure it as just microamps going into the core power on the target chip. And after you've done that, you can change that instruction from no op to, let's just say XOR. And then you load all of the data stack with minus ones. And so now every time you do an XOR, the top 2 elements of the stack are minus ones, and so that'll replace T with a 0. And S, of course, pops a minus 1 into it, so that the next time you say XOR, it will in fact turn T into all ones. So that will be flagellating all of those lines going up into the memory at maximum speed in an infinite loop. And then you measure how much power it takes to do that. And it's a hell of a lot more, very hell of a lot more. And as a result, next time we lay out our chip, we are not going to be flagellating all of those lines every time T changes, especially consider that a lot of applications never do a memory write after they've loaded up. And so all of that is totally wasted energy heating up the transistors driving those buses. So these are things you discover after you dink with the chip a little bit more, like the other kinds of things that are a surprise, which is if you just move the code around a little bit, the amount of energy it takes per unit useful work changes. The current being consumed changes. Because what happens is that as you move the code around, depending on the execution pattern of the code, the number of memory address lines being changed as you move through the code changes. And so it can make a noticeable, measurable, very measurable amount of difference in power consumption to just move the code a little bit, which is also a fascinating thing we learned. There are a bunch of other things we plan to change, but they're of the same ilk. We've learned now that we have a very efficient chip and a very minimalist chip, that it still is using more energy than it should, and so it can still be improved. It's the process node has not been tapped out, and because it remains the cheapest process node to work in, and it remains the lowest leakage process node we know of that mere mortals can afford, because as you go to smaller geometries, the leakage per transistor increases faster than does the speed of the transistors. This is the drive capability of the transistors. It's a phenomenon that goes on as you reduce the geometry. The capacitance of the metal lines does not reduce by the same linear factor as does the strength of the transistors when you scale a geometry down by, say, a factor of 2 or a factor of 10. And so as a result, the transistors get relatively weaker compared to the loads they're having to drive. And so they have to diminish the amount of oxide in the gates on those transistors in order to make them commensurately fast, so you actually get something out of the effort of reducing the geometry size. And the result is that because of the lower oxide, the leakage is enormous. It's fabulously huge. Now it may be, and according to the numbers published, it looks like it probably is true that once you're down to FinFETs, you're into a domain once again where the leakage is not as dramatically huge as it is at, say, 28 nanometers. And maybe you could get some advantage out of it, but what it costs to use that process is beyond the scope of anything we can imagine a way to finance. When the first time I asked Global Foundries about FinFETs at 14 nanometers, they told us it's very fine. We'll be happy to let you see the design rule if you give us a deposit against a prototype run of a mere $25 million. Thank you so much. And it's, I mean, it's funny. It's very funny. At any rate, we can still do things at 180 that nobody else can do anywhere. And that will probably remain true until someone else in the world starts believing Chuck. Meanwhile, we have an advantage, a huge advantage, because we do believe Chuck. At any rate, while we continue to search for volume customers, and while we continue to hope that, for example, Augustine will pull off something cool, we're continuing to work on PolyCells. We found a company that aids nonprofits in getting funding, and so we are going through the reading matter that particular company requires that we study before talking to them. The reading matter is basically focused on the notion that you can't get money into a nonprofit based on emotions of need anymore. You have to actually show a return on investment in terms that are actually valuable to the person that is investing by donating. I mean, it isn't enough that they don't get taxed on the money they give to you. It's because they want to accomplish something good for the world. And we think that teaching kids that designing transistors is not something that you have to spend 8 or 12 years in college to learn how to do. And we like to teach kids that programming is not something you need to spend 1 year in college to learn how to do. And that's basically the goal of PolyCells, is to show that the emperor has no clothes in that respect, and to teach high school kids to do both of these things. And that's what we intend to accomplish, and that's what we're seeking to raise money for. The latest development on that, I may have mentioned this last year, but there are enough people who have made complementary processes that can be implemented with inkjet printers and suitable composition inks. That somewhere in there, someone has done a good job. And what we think that PolyCell's greatest way to contribute to the competency of kids in our country would be to develop one of those processes to the degree that it is replicable and can be installed in an institution of teaching kids, along with people that know how to teach that, and get the kids basically one-day feedback for their designs rather than 10-month feedback for their designs. And to be able to implement one of their designs in something that they can test for a hell of a lot less money than using actual silicon or using, for example, any of the thin film processes. I know of one in UK. The problem is you still have to spend 10 grand to make a mask set to use that process. And there are a couple other reasons why that process is not optimal, but the main thing is the time delay and the cost are still high. There are inkjet printer manufacturers who are proud of the precision with which they make inkjet printers that are used in these experiments by graduate students, typically. And that's what we're after, is raising enough money that we can start teaching kids to program and start teaching them the fundamentals of silicon design while working out a process like this that is not actually silicon and is not that fast, but has all the same principles applicable to teach them end to end. Okay, you can design something, you can get something out, you can measure it, you can watch it work. And you can do this in a short enough period of time that the feedback hits you before you forgot what you were trying to do. So that's the goal for PolyCells, and maybe we will succeed in getting some funding in 2023 for it. And that's about all that I have to say that's in any respect new. Does anyone have any questions?
If there are no more questions for Greg, okay. I think that we'd like to thank Greg very much, and we're very grateful that he came today to present. I would like to ask Greg one question before we let him go, and that is, if I wanted to play with a GreenArrays chip or get started learning about GreenArrays, what would I do?
As somebody who is technically educated, let's say that.
Some fourth weeding.
Yeah, go to the website, download Array43, write code and run it on the simulator.
Okay.
We have a simulator that can handle 2 chips.
Would you be willing or interested to make a short video that we could show at a future meeting, showing, maybe some uneducated doofus going through those steps of beginning to learn about GreenArrays?
Yes.
Okay, we'll hold you to that. I'll be in touch. So we're going to take a short break. Here's how you